Welcome to chapter 5, the final chapter of this class. Only 3 sections left, okay? Exponential growth and decay, some other section, and then a really cool section in 5.3. I'm recording this video early, so I actually don't remember what our other section is for this week, but you do, because you see it on Canvas. Okay, so we're going to start with a theorem, and then we're going to talk about a bunch of random stuff. Baby differential equations here. Differential equations are actually a very complicated area of math, but we're only doing baby ones. Should be fine. We don't have a lot of theorems in this class, but here's a theorem for you. If y prime is equal to some constant times y, if the derivative of a function is just the function itself times a number, then the function must have been of this form, ce to the kt. That's our theorem. Small version of the theorem. The book has a wordier version, if you'd like. So let's kind of verify this, or kind of look and see kind of how it works, right? If this is our function, right? Let's do a little check. It's not perfect logic here, because but let's kind of see that this sort of makes sense. If y equals some constant times e to some other constant times t, y prime, we know is going to be k times ce to the kt, right? The derivative of an exponential function is itself multiplied by the derivative of the inside. Derivative of the inside is k. Well, this is y. So we really do have that y prime is k times y. All right. Exponential functions have the special property that their rate of change is proportional to the function value. Okay. We also sometimes say the rate of change is, what's the wording? We'll talk about it later. I don't remember where it is. There's a specific wording that we're going to use for that. So this k value, is what's known as our growth constant. If it's exponential growth, this is the growth constant. We use that word every once in a while. Okay, let's solve some differential equations. Let's use this theorem. All right. Example 1. Find all y of t, find all y that are functions of t that satisfy the following. Part A, y prime equals 0.3y. Ooh, the theorem. Let's use it, right? Is this of the right form? Theorem says if y prime equals k times y prime is a k times y. And what is our k? 0.3. So we do have this case. Then y must be of this form. So by the theorem, y is ce to the kt. How convenient. Y is equal to ce to the kt. And what's our k value? Our k value is 0.3. So y is some constant times e to the 0.3 times t. We don't know what the constant is. It could be anything. It could be 2, 5, 7, 12. We don't know. But remember, we're being asked to find all y that satisfy this. So yeah, one of these answers has a c value of 1, maybe has a c value of 2, 3, 4, pi, e, 27, negative 1. So that's a lot of answers. We're done. Just like that. Okay. Do part B. Find all y that satisfy this. Y prime equals 3 times y. And y of 0 equals 2. This is what's known as an initial condition. Okay. It's an initial condition because look at what happens. Oh man, I ran out of space again. This tells you the value of y when t equals 0. When t equals 0, that's at the start. Initial condition. No time has passed. All right, so again, it's of the right form. We're going to use our theorem again. This time our k value is 3. So we know that y is going to be c e to the kt. And we specifically know that k is 3. The difference, why this is not our final answer anymore, the difference between the previous problem is we have that initial condition. So there are infinitely many answers depending on the initial condition, but once we have an initial condition, we can find our c value. All right, so we're going to use this to find c. So when t equals 0, y is equal to 2. Right, t equals 0 is when y equals 2. That's what that initial condition says. So we plug it in. Y is 2. That's equal to c e to the 3 times t, which is 0. And remember that e to the 0th power equals 1. So this whole thing is e to the 0th, which is 1. So we're just going to get c is equal to 2. So all the numbers, all the functions, rather, satisfy this requirement. There's only one. 2 e to the 3t. And we can check our answer. If I take the derivative of this function, is it 3 times the original function? And it will be. Okay. When t equals 0, is this function equal to 2? It will be. You don't trust me? Go ahead and check it yourself. Let's do one more. Part C, one more differential equation. Y prime minus ky equals 0. Y of 0 equals 10. Y of 1 equals 20. We don't know what k is. It's not in the right form. We have two conditions. We have an initial condition and another condition. What's going on here, Jason? Stay tuned. Be patient. We'll find out. Let's revisit the theorem. If y prime is k times y, then we know the solution. So let's try to get it that form. We want y prime to be in, I'm not going to write this down. Well, to get y prime to be k times y, we just add ky to both sides, right? Now y prime is literally k times y. Ah, okay, now I can use the theorem. So y is going to be something of this form, c e to the kt. We don't know what k is. We don't know what c is. But luckily, we have two things we need to find, and we have two tools for dealing with that. So start with the initial condition. Let's plug in that initial condition. Again, that initial condition says that when t is equal to 0, y is 10. So y is 10. T is equal to 0. And I still don't know what k is. But it doesn't matter. Because this is e to the 0th power. And e to the 0th power is always 1. We're just left with c equals 10. This gives us that y is equal to c, which is 10. E to the kt, we still don't know k. We're going to use our second condition, that when t is 1, y is 20. Y is 20. T is 1. Let's find k. Okay. Divide both sides by 10. We'll get 2 equals e to the k. We have to solve for k. We have to undo the e. We're going to take the natural log of both sides. The natural log of the left-hand side equals the natural log of the right-hand side. You may need to review solving exponential equations. I have videos from last semester's 1400 class if you'd like. College algebra. We'll get natural log of 2. Again, natural log and exponentials are inverse functions. So that's our K value. We found K. We found C. We're ready to finish the problem. Y is going to be C, which is 10. E to the K, which is the natural log of 2, times T. That's our answer. Fun fact, this is also 10 times 2 to the T. It's another way of writing this problem, this answer. But you can just stick in the box. It's doubling every unit of time. The doubling time is T equals 1 unit. We'll talk more about doubling time later, though. I think we do anyway. Or I can talk about it right now. But I won't. I think it's the next video. Anyway, good joy, good luck, enjoy. Have a good time doing some math. I know I will.